and they're more static too, so they're like more drony. And then there's a microphone, which we're probably not going to use today. And then the last, wrapping over this corner here, this area is going to represent the 8 buttons, and those are like in 8 bits. So it's actually just looking at as a byte, but each button is 1 bit. It's a button. So those are the signals you get on it. And so to sonify those signals, actually, oh cool. So this is the patch we want to get to, but we're going to actually go back and just try to make a patch from scratch. So this is, you could program in the command line too. So I could go to Mac. It has Linux, Windows, and Mac here directories. I could go in there and I could run. Oh, this is a Windows, it's not a Mac. And then I could run. How do you call it on Windows? So Lisp. And then that's ready to take code, and I can do a spit out of the values that are coming from the device. And then I could just upload code on the command line. And code for it looks like Shibobo examples. So here's this patch that is playing right now is this one. And this is what code looks like. It's called Chalis. It's the name of the language. It's based on Lisp, of course. And that being that, it's like a DSP kind of Lisp. So you have open parentheses means start an expression of a sound expression, right? And then the first opcode in this expression is the name of what kind of sound DSP opcode that you're accessing. And so it's just like Lisp in that sense, is that you have the name of your, what should we call it, module at the front, and then you have some parameters, and then a module can take other modules as parameters, okay? Now, so this is messy because it has, Lisp naturally has all these extra parentheses at the end. So that's why I have these programs. There's fish and there's jish. Jish is written in Java, and this is going to be the same thing. Fish is written in C. So it should run on any kind of computer because you can always run the Java version. The Java version uses the command line, and the C version has a built-in command line. So to make a patch, I can actually just type directly into here. I zoomed in. I'm going to make a. It actually uses Chalis actually uses all 4 versions of closure. So I have a curly bracket right here, and that means that I'm writing a patch. You can have more than one patch. So say if I exit this patch and I make another patch, then I can have, they're like presets, and you can switch between presets live, okay? So, but we're just gonna work with one preset for now. Now I put a parentheses there, okay? And then now I'm gonna put, inside the parentheses, I'm gonna put, horn is a triangle wave. Just accept that. And then I'm going to give you, I'm going to give 2 random numbers that gives it a random pitch. And we'll go into this later. But now I just have, to go out the left, I have to put left. So I want to put that inside as a processed parameter to left. So that's putting it out the left speaker. There's also right, R-I-G-H-T. There's left and right. And that's your stereo, it has a stereo output. So now I'm just going to actually upload this patch. So there's a horn at 55 and 19. Now I can explain those. Yeah, also the C program crashes more because it's written in C. But it's never crashed on the first one. Look at that. I have to like do the whole thing here. Control-Alt-Delete. But no worries, I mean, whatever you want to do, fish. Okay, start this again. Oops. Maybe it's because I'm looking at the screen at the same time. So, I'll zoom in again. Make a patch, make a left, make a horn with 2 random numbers, upload it. Okay, now we're just going to change a number. It's changing the pitch. Right? Change this other number, and I don't have enough voice to explain Num and Dino today. I should try. There are 2 parameters. They're very natural parameters of an oscillator. A normal triangle oscillator, as you would experience it in a surge or whatever, does not have the Dino. Dino would be set to a certain number by resistors inside the module. Dino is denominator. Num stands for numerator and Dino stands for denominator. Numerator you can understand as a synthesizer person. Numerator is just the speed of the triangle wave. Okay, so I'm going 32, up an octave, right? And then, well, I can't go to 128 because we're in bits here. So let me start with 10. 20, 40, 80. You can hear they're in octaves whenever I double it. So that's the speed of the waveform, the triangle waveform in space. But the denominator is the width of it. So if you look at my hands, I have a triangle like this, has this width, right? But then if I shrink that width, that same speed is actually going to manifest a higher frequency at a quieter volume, which is interesting because it's it's like a filter and it changes the frequency. So I'm changing this Dino. It's getting higher, but it's also getting quieter, which is interesting musically. It's better than getting higher and louder. That would be bad musically, you know. Higher and quieter is cool. So these 2 parameters are just like natural. They entstehen from the code. They arise from the code itself. And so I decided to keep them. Now, if I want to change, now I'm going to put a bar as a multiplier for this. So now it's silent. What I have to do to play it is press the bar. Bar A. So bar is at 0 right now. It's multiplying a horn by 0, so it's silent. So I'm giving it values, and then the same thing with, it's just a system of like bar A is just bar, and then there's bar B would be the second bar. So what I can do is duplicate this a few times. I can make horn B, because they have to. It's a very embedded system. It's not threaded or something. It's very silicon, like bare bones silicon. So everything has these like B or C. There's just these set instances that you can have of each oscillator. But by the way, you can reference oscillators to your heart's delight. You can call them as many times as you want. Bar C. So now I have 3 bars and 3 oscillators. Well, I should do different pitches, right? So 40, just random different pitches. Okay, so I now have A, B, and C on these 3 bars. Okay? And then there's filters, there's all kinds of stuff. And we'll get into that. I'm just trying to show how you wire it up, basically. Maybe I should do the... maybe a little bit different opcode, like saw. Although I hate saw, right? Saw. And then we'll do it by the corp is the antenna on the back. So now I have this antenna. Oh, other side. Right. And I'm playing the antenna on the back. So you can see that in this. Delete that. So So you can see it's pretty simple to just wire up gestures to oscillators here. Okay. Does anyone have any questions at this point? And then if I wanted to, I could. Here's that thing about the different presets. I just duplicated it, and then I could edit this code here, or change this one, and I could make it lower, just one thing different, and I upload that one, or I upload that one by double clicking on it. So this has a different horn than that one. So, and then they can jump between each other. So let me just show let's do some examples, I think. What's this? The latter one is cool. They're all kind of random. Oh, it is not having a good day. Well, that's why I should switch to the Java version. I wanted to not do that code yet. Let me just show some examples first. Extreme yelling. Oh, so this actually uses a new feature to the Java version where it can have like randomized values. And so let's just see what it is first. Oh. I don't know what it is. I'm just experiencing. But there's an LFO for sure. And it's random. So every time I upload this, I'll get random versions. And that's from these white things. This is the random symbol. And that's on the computer, not on the device. This is just a way to experiment with programming all kinds of different patches with randomized values. So, sorry, I'm just using this tiny speaker to try another one. What are all these? I don't know what they are. I'm just going to try them. Just limit. Oh, this one looks crazy. Might not work. No. Oh, because this one doesn't actually make sound. It's just checking code. Okay, well that's a random. You can also see what the code compiles down to in this window here. You can see it compiles down to just every time I uploaded something, it called the program Chalis.exe, and it pre-compiled it into numbers and expressions, and then it just became bytecode in the bottom. And that's what was transmitted to the instrument. And that stays in the instrument. You can unplug it and play it. It has a battery. And it has that code, stays in it. And then, for this one that I just was demonstrating, it actually didn't create any code. It was like a test patch of Lisp. So what's dog breathing? It's, again, using this random maker thing. Well, I don't know how. I can't. Maybe that's just like a shred of something. It's not supposed to be there. I wonder what that's supposed to be. Let's try horns. Oh, that's cool. Oh, that's just a lot of horns, which are triangle waves. And they're like permuting somehow. SHNTH. Oh, yeah, okay, so here's more of a normal patch. This is like a patch from 10 years ago. I'm going to upload it. I wish I could play it in the speakers.
You can.
Maybe later.
Okay.
Okay, so you can hear it's trying to emulate a beach. So I'll just try to just say what these opcodes are. Of course, we're going out the left speaker, and do you see how everything's nested? This is not like Max MSP where everything's wired. This is Lisp. This is actually representing a one-dimensional stream of text. So you can't wire things like in Max MSP because that's a two-dimensional code. This is code like C and stuff or Lisp. It's a one-dimensional stream. So the way you have things feed into each other is you have to nest them. which is great. It's not a problem. Especially when you have a program like this, organizing your parentheses. That's why this program's there, to make expressions more like natural feeling. And the reason it's called fish or jish is because they're like, the programming model was to have fish within other fish. So, but it's very abstract. So mount is a LFO, like a mountain, like a triangle wave at mountain frequency. And smoke is noise. And wave is what physicists call a resonant filter. It's a wave equation. So it's filtering noise, and then it has LFOs at these different frequencies change. The Q is set to a pretty high value, which means, Q at a low value is actually resonant, but so a Q at a high value is less resonant. You don't want a highly resonant beach. So, and then, the program tells you actually kind of what each value is going to be used for. So the wave has an input, which is smoke, and then here's the Q is set to a certain number, and then its rate or its frequency is being controlled by an LFO here. And then this is how you would jump from this patch to this patch. So I'll push that one button. Oh, right. I actually jumped from the bottom patch to the top patch. There's only two here. Because the bottom patch, if you hear, listen, I jumped again. You hear it has those little sparkles, those little sounds. That's called, this patch is called beach lanterns. So it starts in beach, which is just the sound of the waves. And by the way, it's going out left and right at different kind of variations are going out left and right. So it is very stereo. But the second part of the patch down here, which I just triggered, has this clause in it, which uses fog, which is short for 4 grains. So it's like kind of really primitive, really embedded granular synthesis. And it's being triggered by dust, which is random pulses. And then it has some parameters for the frequency and the shape of the envelope. Oh, by the way, here's sample rate. You can change the sample rate. So if I change this, 36, 1836. Now it just went down an octave. Okay. Let's look at some other patches. There's some really complicated patches here. Here's emulating a drum machine called the Plum Butter, which is what we sell here. So this actually, the last one and this one don't use the bars at all. They're just doing synthesis on the chip. So it's doing all kinds of stuff. It has, I'm controlling the lights on this one. It's doing some kind of showing where the LFO is with the lights. So that's cool. You can send stuff to the lights there. I don't have a scroll bar there. So here's the stuff that's going out left and right. And there's another patch, but we'll just look at the top patch. So left is getting a horn, which is that triangle wave again, but it's being multiplied by sauce, which is a low frequency. It takes something in, but it only computes it at a fraction of the rate of the other one. So it slows stuff down into really slow, like LFO range. You could take an audio frequency thing and slow it down into really low frequency ranges. Oh, and this is taking something from a corp, but I'm not hearing it. And this uses references too. Now, I'm not going to do any more of these because they're probably not helping, but you can see what a patch would look like, once you play around with it. everything is like completed. Everything is contained within. You see, everything's contained within one preset boundary, right? And this program does it automatically for you. Everything's enclosed in this. This is a preset, you know, and then here's another preset down there. And then there's a left and right expression. And you could have stuff outside the left and right, and that you just won't hear them. But it's good to organize your code to have stuff outside the left and right. So for example of that, let me try to make another one from scratch here. Left horn, okay? So how do I operate horn? Well, outside of that, I'm going to put horn here, the same horn as horn A, and then I'm going to give it 2 random numbers. So this is a reference to the horn that's being computed here. So to show that it works. Okay. Oh. Okay, I've made it quieter. But so yeah, this is a reference to the horn, and the horn's actually being like run here. So if I put another horn B, you won't hear this. I'm just doing random numbers again. So you don't hear it. But if I put going with the reference theme, I could put horn B there, and now I have a feedback system where it's creating like a complicated wave. And maybe if I want to put it here, reference to the first one, now I have kind of a loop. But of course, it depends a lot on the other. Well, maybe I'll do the antenna. Whoop. So now I'm kind of controlling one of the frequencies. And maybe I'll control the other frequency here too. So this is how you would make like a noise box, by kind of feeding everything into everything else, right? Right? So now we have a lot of data sounds just out of 2 horns and referencing each other. And again, you're just hearing this one. Okay? So how would we do the filter on this, right? So how about I do wave is the filter, and then I put horn as the input, just a reference to it. Now I'm asked for Q. Well, I'll just put Q at 1. I'll make it drippy this time. And I'll put bar as kind of a frequency thing here. So now you don't hear anything because bar is at 0, so it's like at 0 frequency. Now I'm playing with the bar. A little bit too resonant, right? So I'll turn that Q. I could put, maybe I'll put bar B for the Q. Oh, I have to make it work, you have to actually reference another code, you have to have it in parentheses. The only thing you could put outside of parentheses is numbers. That's not a number. That's not. You can put numbers, just can sit by themselves. But to reference another thing, it has to be in parentheses like that. So now I have the Q there. So it's like a squishy noise box. Okay? So, any questions yet? At any point here?
Is there like a difference between the negative and positive values?
Well, good question. So the SHNTH actually operates in 2 modes. And they're modal, so you can switch between them at any point. signed and unsigned. And to get it, so it's by default it's in unsigned, and then you could switch into signed by calling Arab, which is a reference to the early Arab mathematicians did not use negative numbers. And very early theory of Arab math. And then to switch back into signed math, you call it Dirac, which is named after the physicist who invented or discovered the negative side of physics, kind of, as I understand it. So it has those two modes. So negative numbers in Arab mode would be interpreted into just a higher number. Like -1 would be 255. So actually negative numbers are handled pretty well. Like you don't really even need to worry about if it's negative or positive. Yeah. So yeah, it's as smoothly as possible. Like, and well, actually, let me just show you in another way. So say, just to prove it, I would go left, horn, 32, 32. Okay. Oh, I have to double click on that. So, and then if I put -32, up, -32, -32. Oh, interesting. Oh, that was because I didn't click there. So it's the same thing. It just, yeah, I didn't want negative numbers to be a problem. So they're just there. And remember that all this code does get boiled down to just bytes. So everything is just bytes in the end down here. They are different bytes. There's -32 is 224, and then the one before it was 32 and 32. But the processor handles itself because there's negative signals coming from the bars too. So yeah, if I keep that one and I just change that to a bar. Now it's at 0. The bar's at 0. I'm going to press it. It's going to go up, and I'm going to release it. It's going to go through 0, and it's going to go up again. So there are two going ups there. So yeah, negative numbers, just like in real, well, I was going to say in real life. I mean, real synthesizers do have a difference with negative numbers. But that has to be, like analog synths would be, like if you go negative, that's just more lower frequency. And you can rig it here too, to go a lower frequency. Also, you can't have, I've been working for a very long time to try to make a wave equation, the resonant filter, in unsigned math, but you can't do it. It's like you can't do a filter without negative numbers. So unless you do some kind of tricks or something. So any other questions or like?
Is there a way to scale the range of the bars?
Yes. So that has to do with the mul and add. So I'm gonna add a parameter here. And the first parameter that you usually get after you get through the meat of a, so like here's like the horn, here's the meat of it, or the vegan tofu of it, is the numerator and the denominator, and so that's like the actual like operating parameters of it. And then the first two parameters on most opcodes that you get after that are mul and add. And if anyone knows Super Collider, that's how it is in Super Collider too. So, and that's reflects a basic core, like fact about computer music is that multiplication and addition are like, and physics, just everything mathematical, physical about the world resonating, always has. You always want to have some way to like put a multiplicative coefficient and add something else. That's how like like your graphics processor works, your sound chips work, anything works by having mul and add as like very accessible. And the best way to put them very accessible is to put them right there in the accessible right after the main parameters. So I'm going to delete those. And we're working down here on this one. So you asked, oh, it's not barn, but it's bar. So that's the first bar. And then now I put a mul of 43. Well, what does that mean? I'll tell you what it means. If I multiply by 128, that, since we're in signed, we're using bytes here. We're programming it in bytes, but that doesn't mean that it's an 8-bit synth. It's actually a 16-bit, 32-bit synth. But we're sending it our expressions in bytes. So our numbers and our coefficients can't go beyond 128. I mean, negative 128 or 127. That's the range for sine. Now, if you're in error mode, you go from 0 to 255, because you go either from 0 to 255 or negative 128 to 127. It's still a range of an 8-bit range, a 256 value range. And again, there's ways to get really fine. That doesn't mean that that's the finest way to control frequencies. Because, by the way, when you have num and deno as two separate frequency controls, that means that you have 16 bits of control there by messing with this ratio. I don't know who knows about just intonation, but when you have numerator and denominator, that's a way of specifying a pitch, a relative pitch. So I'll get back to that. So to scale a bar's value, I would put, so bar by itself is the same as bar multiplied by 128. That's like full value bar. But then if I want to scale it down, I just put like bar 10. So now it's like a 10 128ths of the range of the original bar. Now what if I add 10? Now I actually have the bar, this pitch in a comfortable range where it starts at 10 and then it goes up 10 and it goes down 10. So it's like this sub-range. So you can hear that it's a low. Well, how about I add a lot? Like add 80? So now it's going to go from 80 to 90 and between 70 and 90. Instead of like negative 128 to positive 128. So now it's like, yes, exactly, we're going to have like this more fine-tuned range. You know, it's just a little bit instead of horn B, compare it. Horn B, bar B, without any scaling. Okay. So now I have, this is the B. It's almost like, it's too wide. But this one is more like a tremolo or something. Okay? So that's that question, right?
Yeah.
And then I wanted to say something quick about just intonation. But we could get lost on this. So basically 40 over 40 is going to be the same. You can drag and drop things and stuff. Horn B, this is going to be the same note. Oh, they're canceling each other out. Oh, no. It's just, they're louder. That's the same note, but just louder. Because it's a ratio. So this first note is 40 over 40, and this note is 80 over 80 in their relative pitch space, whatever pitch space they're in. You could change that with the sampling rate or a lot of other ways. And then, so yeah, if like 41 over 40, and we'll have some dissonance, right? And then 79, now I'm doing more, well, yeah, they're close, but they're very very close. So phasing at a very slow frequency. So with these two inputs to each one, you get a lot more play in the pitch space. And you have two inputs too, so it's convenient. You could send different things into them. Okay? Any other questions? The questions are good. Okay. Well, should I talk about how we emulated? Should I talk about this whole Rob thing?
Sure.
Okay.
Just a question. How many horn or like the oscillators you can have for?
Yes, there's a list. There's 8 horns. Well, just to answer, I'll just answer your question. Let's go across. Wind is the microphone. This is for the other instrument. There's a Persian tar. We have a I'll get it. I'll be right back.
I brought one there.
Oh yeah?
Yeah.
Well, I can.
Hey, if you want a chair, there's one more chair back there. I think it's this black chair. It's behind, yeah.
The guitar.
Sit there, yeah, sure.
And so this has the same, has also 8 bytes of gesture data, but in a different way. There's like 32 frets. And then, so that's 4 bytes. There's 2 pressure sensors here. These are like bars, and there's 2 knobs. So it's a different system, but it's reflected here in the code. This is wind of the SHNTH, the microphone of the SHNTH. This is the finger of the sitar. This is the antenna of the SHNTH, and so on. So these are all kind of like the gesture inputs up here. This is the top knob of the sitar and the bottom knob of the sitar. And they actually would work, the patch, if you write a patch for the SHNTH, it could work on the sitar pretty easily. It'll just change the what inputs are mapped to what. So those are all the kind of like gesture stuff, and I could get into that later. But here's horn. There's 8 horns, 8 saws, 4 toggles. That's like toggle switch. Like it takes, if it's triggered, it goes up. If it gets triggered again, it goes down. It's a flip-flop. Togo is like a sequencer. I'm using it here actually. And that there's like 4 of those. There's probably 8 swoops. It's between 4 and 8. There's 8 mounts. That's the LFO triangle wave. It's probably just 4 smokes because that's noise, and you don't need 8 noises because you could use noise again in a different place, and it's the same thing. You actually only need 1. There's like 4 or 8 dusts. Those are random pulses. Maybe I should explain a difficult thing like. There's like a difficult thing like dust. I should illustrate it. So, left horn. I'm gonna do it like to sonify it kind of, and then I'm gonna multiply by dust. And it takes speed, so I'll give it a low speed. Can't hear it because it's bass. Oh. It's making random clicks, and that's a good thing for like triggering, especially for triggering granular synthesis when you want things to have a scattered phase. So that's why dust is next to fog, which is granular synthesis. And fog takes a lot of parameters, just like normal granular synthesis does. Haze is granular synthesis with a saw wave. There's 4 of each of those because those are computationally intensive. And by the way, when I say that, this is all on one chip, so it's so compressed into this space. There's no floating point computation on this. It's all just with ints. But it's not an Atari. I would say that it's not an 8-bit synthesizer. So I could explain more about that, but I'll just blanket with that. There's the string is like a. I could play string real quick. String is a way to make a string sound. String. Oh, I'm having. Okay, let's try this again. String, trigger. So we'll trigger string with dust because that's a good random trigger. Dust at like a low speed or 4 or something. And then I think I need to give string a speed, a numerator and a denominator. Okay, let's try this. It's quiet. So there's a string sound. It's Karplus strong. It's based on a short delay. But it fits in with everything else. And then comb is actually just a comb filter, like a delay, a short delay. Zither is is 4 strings wrapped into one opcode. So it's like a granular synthesis with strings. So you can play 4 at once and like flutters of stuff. Here's the wave. I think there's 8 wave. There's between 4 and 8 of all of these. So there would be at least 4 filters. Water is 4 filters in one opcode. So it's the sound of water dripping in the bath. Like, actually, I can probably just replace string with water and see if I can get Q and rate. Let's see if that works. Well, I need to give a random rate because I want them to be. So if I speed dust up, you can hear they overlap. So just with one opcode, it's the idea, it started with fog. It's the idea that, in computer music they have granular synthesis based on particles that overlap. So I did that with triangle waves, and then I'm like, well, why don't I do it with a string and make a zither? Why don't I do it with a wave and make a water sound? So it's a little bit more computationally intensive, but you can see this cheap way to have like these overlapping particles. Now we have salted horse, which salt is a high-pass filter. Horse is a weirdness oscillator. I could go into it, but not. No. Slew is a rate limiter, so it'll smooth things out, just like a slew would be on the surge. Wheel is something that you can give it values and push it up, or you can push it down. It's a solution to having a knob without having a knob. So wheel would be something where you could push on one bar and it'll go ooh, and then you push on another bar and it'll go ooh, and you could set different set different values depending on your situation. And then gear and pulse are about processing pulses, like pulse dividers and making beats, like longer rhythms. Sauce and salsa are about sample and hold and processing things at lower frequencies, lower speeds. Melody is a delay of a melody. It's like a CV delay. and Worm is deleting that. These are higher level. Those are for the sitar. And so is scale and ladder, but they're available for the SHNTH. Scale is something that you could put a number into, and it'll imitate the scale. It'll give you a value that would imitate the frequencies that you needed for the scale, which is not 12-tone equal temperament, it's 17-tone equal temperament. Because it's trying to respect the tuning systems of Islamic music or Persian music, where you have neutral intervals. They're neither major nor minor, they're in between. So this is a whole thing. It's a whole separate thing. Press is a compressor. Leak is leak's DC offset. These are wave shapers. Reflect return. There's and XOR. Those are kind of like byte beat processors. This is how you get -1 but you don't ever use that. The reason is because each time you have a parentheses, open parentheses is -1. And that's how it is in some versions of Lisp too. Closed parentheses is 0. So those are kind of like reserved values. If you ever need to use 0, it's pretty easy. You just type 0 into the program, and the code will process it itself. But here, I'll type 0. If you ever need 0, because remember, 0 is a closed parentheses. So if I type 0 and upload that, well, first of all, we'll hear nothing, and then it said 0, and then but it made it by doing this. I'll show you how it made it. It made it by doing that. It made an actual closure, and that became 0. So that's if you actually need to use 0, which you never need to use 0 when you're programming sound, unless you want to have a Q of 0 on a filter, because that's how you get a sine wave. So I'll show you that. So let's do this wave, and we'll do an input. Well, let's do an input is a button. So the buttons are called minor and major. And then now we'll do a Q of 0. Interesting thing we're getting on here. Oh, and I need to give it a rate. Oh, Q. And I did it I could either type 0 there, or I could have, I did this thing here. Let me just give it a random. Okay. So this should be a sine wave once I trigger it. Nope. Maybe it's a low rate. Oh, maybe I don't have a... Well, let's see. I'll have to figure that out later. Someone did that. Why wouldn't that work? Well, maybe I should type 0. Because, you know, if you do a Q of 0, that makes a sine wave. Well, I'm having trouble with my sine wave today.
Might just be. Yeah.
Oh, you know, I think I do need the pot here. I think I always have to have my preset pot here. Oh. Drag and drop. Put it inside a preset. Nope. Oh yeah, that's my sine wave. So maybe I'll move this sine wave around. That's just by ringing. It's ringing. Well, that's going to be... I don't want that kind of sine wave. I'll do a mount. I'll do it. I'm just giving an LFO for it, so it doesn't get in the ears. Okay, so yeah, you can hear it's a sine wave, and it's made by getting a resonant filter and giving it a Q of 0. That's the only time you need 0. That was to get back to that reason why you have 0, because a Q of 0 in a resonant filter makes it ring forever. Okay, and I triggered it by pushing this minor button. Because it was originally, with a Q of 0, it could either be at rest, like completely silent, or it could be ringing. So I had to bring it from being at rest. So, okay, well then I'll try to finish this list of opcodes. There's left and right there. Those are the outputs. Square takes something in and it makes it into a square wave. So it would take a triangle wave and make it into a square wave. It's a comparator. It compares. Modo is modulo, so that's like making things really loud, and it's like a wave shaper too. Here's sample rate, and you can hard code multiply and add. There's situations where you need that too. This is a button. This is an orange button. It's just another button available. And bend and jump are about jumping between patches. Pan is like left and right, but it sends things at different proportions out, left and right. And then here, this is how you get a 16-bit number with two 8-bit numbers. So if I wanted to give it up, looking at the screen, okay, short means 18-bit, I have 16 bits. So I give it two numbers, and now if I tune the small number, it should go, you probably don't hear it, but, well, I'm not hearing it because it's so small, the difference. Yeah, I gotta go from like 1 to 100 to hear it. Oh yeah, it just moved a little bit. So that's how you get, that's one of the proofs that this isn't just 8-bit numbers, because this is taking two 8-bit numbers and making a 16-bit number. The main DSP line is 16-bit, which is enough to avoid sounding 8-bit, but also enough to allow 8-bit sounds to happen too. And then this is that thing I mentioned earlier about signed and unsigned math. And lights is how you send a signal to the lights on the top there. So yeah, you asked about how many there were of each one. So it's basically, well, in the main opcodes, there's between 4 and 8 of each one. There's actually just one left, and there's one right, but you can call left as many times as you want to send something out the left speaker. But yeah, these main things that actually process and hold state, they're between 4 and 8, and it'll tell you in various ways how many. It should, if you go over, the way you do that is just by doing horn A. How did we do that before? Horn A, horn B, horn C. I thought instead of doing like horn 1 and horn 2, I thought that would be kind of confusing and to have a number, so I used letters instead.
But I think
Yeah.
from the previous example, you also showed like the for loops with the horn with I, so that you can add more horns.
Yeah,
like
it was horn. Yeah, horn was A, B, C, D, E, F, G, H. Wait, A, B, C, D, E, F, G, H. I don't think there was I.
Yeah, but then I think
Yeah.
you're doing some sort of for loops that you played a lot of horns together, like
Yeah.
from the.
Yeah, well, that was with the scripted. That was like a scripted composition that would be. There was some Lisp work going on here that generated some DSP code. So the I was actually just like a variable.
Yes.
Here.
Okay.
But then that became. Then yeah, it could become different horn. You could take horn and add 1 to it, and that'll be the next horn. And so you could do that all kind of functionally, like composed that way. Yeah. But yeah, generally the top of this list is the sensors and the gestures. In the middle is the actual stuff that's computed and has state and oscillates and resonates and stuff. And then the bottom is just tool kind of things, like left and right and mull and add. There's no left B and there's no mull B. They don't have any state. They just take something in and they spit something out. So, any other questions coming up here?
Can you write and add your own opcodes?
Yeah, well, so that's a good segue. I wrote, yes, it's all open source. I'll show you the directory. Shibobo directory, it's on GitHub. These are compiled things, so that would be for the Macintosh. There's some demo programs that do other things. Let me see, I can get it going. Okay, let me see if I can open Sauer Harrison Ford. So this is running on my computer. This is not running on the device, on the SHNTH. This is running on my computer. So just so you know, there's examples of stuff you can do on your computer to take the data from the device, those signals, those 8 signals I showed you, right? These signals are always being streamed to the computer. So you could bring that into Max MSP or Super Collider or whatever, and use that there. And I also wrote a program, just programs in C to do that. So, and those are all in the source too. Examples has, most of it's in Chalis. So, software licensing. So that's Chalis. And then here's the source. By the way, there's a tutorial that you can, when you're in Fish, and I'm wiring it up to Jish. But if you need help, there should be a way, if you double click on something, if you spelled it right, and if you double click on it, it has a little tutorial, a basic tutorial file. So that should help in Fish. And that was this tutor directory. It has an example for each opcode. And then in source, here's the source for Fish in C. Here's the source for Jish in Java. Those are the patch editor programs. This is that thing I had running on my computer. And then here's the source for Chalis. And here's the source for the actual code I call it the matrix, but this is actually written in assembly. So if you want to see what a horn looks like in assembly, by the way, it's not even called a horn yet, it's called a trango. But this is the code. I mean, this is really, really distilled. Like a horn is like 16 lines of assembly, what it boils down to. And that's how I could fit. I wanted to fit like a lot of sound onto a simple chip. It's not a cheap chip. It's an STM32F. It's an ARM Cortex chip, but there was also a goal to not use fixed point too, to not get off in that realm. And because that uses a lot more energy too to do fixed point. And when I figured out this thing about the numerator and denominator, I figured I could do this whole gray area of pitches without fixed point. So that was like a whole goal from the beginning, to make like an embedded device that just uses integers. But it has gray, it has like a lot of subtleties between the pitches. So I actually wrote a new opcode for this occasion. And here it is. It's pretty simple. It's called a Wrangler. And that is a synth maker who was a mentor of mine, passed away recently. His name was Rob Hordick, and he invented a few devices. He's an artist, and he thinks about chaos theory, and he also thinking about synthesizers. And he tried a few different ways to make a performative chaos instrument. and a lot of them actually in the beginning involved like classical chaos, like physics.
Good.
So a Wrangler takes, I think I have here's a blip box diagram. Now this one's really complicated, and actually we're doing a Benjamin, which is a subset of this at the moment. So sample and hold isn't there, and Wrangler B isn't there. But the idea of two oscillators. Okay, we got two oscillators, and at the end we have a filter too. This says twin peak resonator, but actually we're just doing one filter at the end. And so there's two oscillators. Those are going to be known as horn and horn B. And then the Wrangler takes two signals in. It takes one oscillator in as a trigger, and it takes the other oscillator in as the data, or clock and data. And it does a shift operation on that over 8 bits. It's very simple. And then the last bit that comes out of the shift operation, it's not depicted here, goes back in and gets exclusive ORed with the data. So it always creates something different from what's coming out based on what's coming in. And it has 8 bits that are like randomized, kind of. They have this random feeling. Or it sounds like a modem from back in the day, too. Well, it sounds like a lot of things. And a lot of us were actually playing around with this idea of, and I was playing around with this too at the time. And when I met him, it was a great mentor to me because he kind of formalized the philosophical ideas here in his own way. And I liked that, I appreciated that. Taking an analog thing here and interpreting it as a digital thing. These two analog things. Think of these as triangle waves. And interpreting it as digital. And then feeding back this digital representation of it into the frequency control of each of the oscillators. And also the frequency control of the resonator. So that's like this kind of feedback system that incorporates analog and digital, or triangle waves and squares, different compositions of squares. You take, formally, it's just the last 3 bits of the Wrangler, and they're like put through a kind of DAC, a digital to analog converter. So it's basically just like 8 values, but that's enough to create the kind of pulsing chaos that we're after. By the way, interesting thing, putting into a filter a comparator of the 2 triangle waves. So it's like pulse width modulation going into the filter. It makes a certain kind of sound. It's really sweet sound. It's a nice little tweak. So in this diagram, there's a few things unique that I want to emulate. But also, Darren, I think we should just, maybe could you jam? Darren's going to get up there and headbang. Yeah.
Uh-oh. Really? Okay, sure.
Do you want me to do it?
Yeah.
Okay.
Thanks.
Well, so this is like a secret, but I've been designing this, and I want to say that I've been designing this. I've been working on Rob's stuff for a while now. He recently passed away, but I've been working on this for a while, and it's sad and tragic when he passed away, but I also feel like I'm part of a continuum here. When I've been working on my own designs for a long time, but I also feel like I want to, at this point in my life or my career, I'm trying to be part of, I see this moment as a way to respect the continuum of designers and makers and try to just go deep on his design and try to keep it alive. I mean, really. I mean, other people are doing emulations of it and copies of it too and keeping it alive. And so I just realized a version of it that, I mean, I designed it from the ground up, from scratch. And this is a prototype version, so it's all rewired and everything on the inside. But I'll try to give some of the sounds that it makes. Is it on?
I think it's channel 2.
So you have a filter. Let me get the filter going. Whenever you hear a filter moving around like that, that's because the Wrangler's sending is being controlled by its Wrangler. So that's making that sequencing sound. And this is, of course, at a very low frequency right now, but let's listen to some higher frequencies for the oscillators. So I'm going to turn down the Q a little bit. This is bringing up oscillator. Here. Play this for a long time, but you can hear it has a wide range from just that simple diagram. Remember, this is not the simple diagram, but this is just take out, doesn't have that, and this is a simple resonance. It's basically a diagram. So taking that, well, here's the difference. People have emulated the Benjamin. This is the Benjamin. And that's the Blippo box. There's two. We'll make the Blippo box in the future. It's just more. It's bigger. People have emulated the Benjamin in computer music, and you can do a good job at that. And you can do it. It's with knobs, and a perfect emulation of a Benjamin can be done in the computer. Not so perfect. I could argue about that as an analog synth designer, because in analog synths we have like singularities and simultaneities and high frequencies that you could get with high sampling rates, but there's a little bit of difference. But anyway, you can emulate it in a computer. It's not like a mystery to emulate in a computer. And you put knobs on it in the computer and stuff like that. And then, but we don't have knobs on the ship. So the difference here is taking that idea of the patch, what this patch is, and trying to emulate it here, and just seeing where it goes, and using the bars to control some of those parameters, and it becomes a different thing. But hopefully, when I play my one emulation of it, you can hear it has some of the same range as the other one, as the real instrument. So this is my emulation. Left wave. So out the left is the resonant filter. So that's exactly the same. And then, I should go through it. So I told you about how there's a comparator going into the filter. That makes pulse width modulation. So that makes, I should do an example of how that sounds on this one. I think I can get it. It's kind of in there. It's in there with everything else. But if you listen to it, if I turn down oscillator A really low. Well, you can hear the shimmering effect. That's from oscillator A and oscillator B being compared. So the pulse width of oscillator A is going like that. It's like, wow, it's getting wider and thinner. It's getting fatter and slimmer. More nasal. It's going from nasal to full body, back and forth. It's hard to explain on the Wrangler when everything's all wrapped up, all involved with everything else. So, but it's there. So the idea of not just putting oscillator A into the filter, but putting a pulse width modulation is pretty easily done using square. So you put horn, remember oscillator A and oscillator B, and then I'm squaring them, which means comparing them against each other. And I also have a multiplier. This is the volume of the input, and then because I wrote this new opcode, I haven't given it a name yet. Of course, the name would be Wrangler, but actually I'm just referencing it where it would be in because all these names just become numbers in the end. So I just use a number for Wrangler. Here's the Wrangler itself is operating right here, -48. I'm sorry I did that, I didn't put the name there, but it does illustrate something, that if you do write your own opcode, they are just numbers too. The name of the opcode is just a number in the end. So every time in this patch you see -48, that's actually this new piece of code right here running. Oh, and you can see it has an exclusive OR right there. So that's the actual, it's doing some shifting. It's really complicated. Well, it's really simple, but it looks really complicated. It's the opposite of good code, right? So I'm putting this this pulse width modulation into the input of the filter, and Q is being controlled by this bar, which is good. I want to have a squishiness control. And here's our antenna on the back is controlling a relationship. Oh yes, here's the Wrangler, goes into the frequency. Everything's all nested. And I'm also sending some of the oscillator A into the frequency of the filter too. So it's all mixed, but that's actually how it is in Rob's diagram. Here's my sampling rate. I put it down a little bit lower. And then here's where I'm operating the two. They're outside the left, outside the sounding space here, but they're still being operated. Here's oscillator A, oscillator B, and then the Wrangler is actually being shown on the lights of the instrument. So oscillator A is getting some pitch information from the Wrangler. This AND has to do with that he would only use the top 3 bits of it, so that's why there's an AND there. And I'm using a button. This button, so now I'm using buttons and stuff to do things that aren't in his design. So I'm changing some pitches, sequencing some pitches that I can scroll through with different buttons. And that isn't in his design, but I don't have knobs, so I'm trying to have like a little bit of variable pitches. And I could do that other ways too. I could have like random melodies, random numbers, all kinds of stuff. And then here's more of the stuff with just general layout though, but oscillator A, oscillator B, and then the Wrangler takes A as a clock and the square wave of B as the data. So let me just play it and let's see if we can get it. Well, first of all, you can see, turning it up. Maybe I'll play it in the speaker. So that's there's the Wrangler going right there. You can see it's going like across. That's the shift. That's how a Wrangler works. It shifts a bit whenever there's a clock. It shifts it over and over, and then it's fed back into the beginning somehow. And then, oh. So I have my filter on this back, and you can hear the PWM. I think it doesn't just have the sound of a triangle wave going into a filter, it has the sound of like a variable square wave. So I'm controlling just frequency of the filter with that one. That seems like a good one to do. And then I think I put Q on this bar, so I'm like, every time I press the bar, it subtracts some wetness out of it. Like if I let go of the bar, it's back to being wet. If I touch the bar, it's more meaty. And then the other bars were about feeding the Wrangler into the oscillators to create chaos. So if I touch these, it's starting to get wild and weird. And this is feeding some signals into the filter too. Like, I think this back one is changing the filter, rumbling the filter. So, right. And then that Togo is a sequencer, so I can use minor and minor B to change some pitches. And I added another button too, just to like pop. That's the major and major B, just changing a pitch too, adding something to a pitch. So it's interesting. You would think that an analog instrument would have more of a individual character, but this actually has a more universal character because it's just 8 knobs in like infinite combinations, right? And that's actually his goal, is to just do with 8 knobs, like have a whole regime change, a whole bunch of different regimes in there. So that's like a universal thing. But this is actually more of an individual thing. And because the code was just created by hacking and stuff. But another difference is that I always have this patch exactly like this. It's saved. It's a computer music patch. And to me, that's always been, I always needed that as an analog maker to be able to offer that. The people, if you want to make a song or something, this romantic idea of making a song that you can always come back to. And that's what this is. And then you can take this code and change it around and make different songs with it. And it's not a universal thing. It's kind of like stuck in one zone of where this was. So I'd like to do more of it and try to get some of the more noisy things from it. But for now, I can hear the result. So that's how I emulated that. And that has that new opcode in it, the Wrangler opcode. Do we have any questions on this? I think I'm getting about done now.
But that's not out yet, right? It's not finished yet completely, the Wrangler, the opcode?
The opcode? Yeah, it's done. It's there. You just have to update your SHNTH. You would plug it in. And, one thing, if you know Git, you would be in your Shibobo directory and you'd git pull. Or you just download a new Shibobo directory. Because I updated this like last week. and then you would go into Fish or either program, and you have a patch, and then don't freeze like that. Just because it's zooming. Yeah, it's probably my computer too. I'll do it again. Nothing lost. Okay, open. The Java one doesn't freeze as much as the C one, but it never really is a problem, I thought. But okay, so I have a patch. This is the patch that's open in the other one, and I do something called change cuisine, and I go. This is all written out in the notes, but then I get this one in the main directory. This is actually the binary file for all the code for it, so you can update it this way. So I'm going to double click, and now it's actually uploading the whole thing, including the new Wrangler patch.
And in the beginning, you show this new randomization things in the patch. Are they also like part of this update?
Oh yeah, that is already. That's not on. There's nothing new on here for that, but that's just in the code. I mean, I could do a quick try to show you how that would be, how they work. I haven't really even documented it. It's just something I made the breakthrough, and then I didn't really document it yet, but it's. Remember I have to do a left first. Left, horn. Now I do, instead of a number, I'm going to do it's a caret, a triangular bracket. So now, and by the way, if you're thinking, what's the fourth closure symbol is square brackets. And that's for like an array of different things on the computer. So it's Lisp, but with 4 different kind of parentheses, which is cool. I think that's really interesting to me. So this means random, and I think I give it a multiplier. So, I need to. So, I don't know if we're done uploading from the other file. Might need to send it. Let me see what our code looks like here. It should be right. It looks like it's sending. Oh, it's because I don't have audio out. So. It's not that random. It's not that random. It should be random. But 10, 13, 10, 10, 7, 7, 4, 4 is following a pattern. But, maybe I don't know. Well, maybe I'll just do randomly then. It's making a melody. I have to check that. I'm definitely not done with this part. But it's something, this is the example. I'm giving something that's supposed to be random when I'm sending it to the device. So it's the idea that you could like make a patch that has a bunch of random values in it, and then if you find one that you like, you could actually copy it from here if you like it. And then, how would I do that? Something like that. And then I think I can even paste it. Paste text. Does that work? No. It works in this one. You can paste text. Oh no, I can't paste text. But you can paste it into like a file and then save that, and that could be your patch that you like. So, but that's, yeah, I don't know why that, I have to go into that and figure out why that's not random. That should be pretty simple because that's in C. But, and you see how it has like a different color scheme. It's not in colors.
Yeah.
It's in grays. So, and then it has, you can make functions with it too. You can define values, would be defined with that. And then I'm really funky programmer, right? So I decided to only use the symbols above the number keys and like define each one. So there's like, this is like define, oh no, this is define a variable, so it would have like that. Oh, that's a comment actually. It would, and then that would define that as like you could do plus 1 and stuff like that. And then that doesn't stay on the SHNTH. That's all in the computer, and that would be a way to make parametric patches. But I'm not obviously not doing that right now. But it is available, and let me see if I can show you what they are at least. So that would be in Chalis. But yeah, so car, set car, cooter, that's Lisp stuff. Set cooter. And here's add, minus, divide, mul, and, or, that all makes sense. XOR, not, mod. And that's supposed to be random, but it wasn't. It was random before. Define a variable as something. Oh yeah, this is function. Hash is function. And if is a question mark, that makes sense. And these are conditional, equals or less than or greater than. And print is money. And I was gonna do euro, but I couldn't get euro to work in code somehow, like strings or something. But that's what that whole system is supposed to be there. This is the code for the Chalis evaluator. So, any other questions?
Can you mix with the previous pitch, like overdubbing the already sounding pitches? For example, like if you forget to save and then you want to just add a sound to it, can you do it?
Yeah, you could add a sound, but there's all kinds of weird things you could do. You could probably do, now I haven't tried this, but I could go, maybe if I made 2 patches with 2 horns, because it's a different patch, I don't need to make horn on one beat. Oh, like we need to have.
You know where you're going?
Yeah, 2 patches like that.
Okay.
What if I do like, I can't do like a remix, but I could do something that's always jumping between the 2. So let me see if I can make it work. I'm going to copy this. This is bend, like circuit bending. And so hopefully, well, it's not jumping between the 2. Maybe if I do like jump instead of bend. That work better. Now it's jumping between the 2. But that's not really what you asked. You could interleave it that way. If I got it fast enough, maybe I could make this kind of like buzzing interleaving sound. Interleaving is a really cool way of mixing. I don't know. It's like the ancient Nintendo way of mixing where you have like 2 sounds and they go, you know? But, oh, I'm not getting it anymore again. I'm just playing around with it to try to get that to work. Oh, because, okay, 100, maybe if it's 2 or 12 or something. 1 was probably not enough to make it jump. Oh. Nope. Right, as you can see, there's a lot of like playing around to try to get things to work. I'm not getting it to jump anymore. I can undo though. No, undo too far. Well, I had it there for a second. But no, I can't do a mix of them, no. But you can, the way they're supposed to work, the way they're supposed to be is jumping, and you give a button and you multiply it by 1, and then that will bring it exactly 1 patch forward, 1 preset forward. So if I upload this and I hit the button, I'm going between those 2 patches. So that's like the basic thing. You know, if you have a performance and you want to have like 4 different patches. So, good question. I wish I'll work on that interleave. There's so many things that you could work, that I could work on and think on this, but again, like it's the users that really do the interesting stuff. And I'm just trying to facilitate the users. And I think the best thing for a user is to just get patches that are already there, and the examples are that find patches that someone else made, and just change the values is like really the easiest thing to do until you find a value that you like of your own. So, well, thanks for coming. Thanks for the questions. Should we do something else now?